Tonight, we're going to solve a mystery that serious researchers have quietly been investigating for decades using real physics, real biology, and real historical data. Not the question of whether a ship could ever reach another star or Euro. We've stood on that ground before, and the honest answer is, maybe, eventually, if enough gaps in our knowledge are closed. Tonight's question is sharper than that, and considerably stranger. If humanity ever actually built a ship like this and actually launched it, what would be the real reason it failed? Most people, asked to guess, reach immediately for the obvious suspect: the engines. Surely a starship dies because it simply can't go fast enough, or because its fuel runs dry somewhere out in the dark between the stars, stranding everyone aboard in permanent, silent drift. It's a completely reasonable guess. It's also, according to the people who have studied this question most carefully, almost certainly not the real answer. Here's what most people don't realize. Researchers have spent years treating this exactly the way a careful detective would treat an unsolved case or Euro, walking through every plausible cause of death for a generation ship, one suspect at a time, testing each one against real engineering data, real biological data, and real human behavioral data, and then ruling most of them out as the answer, even while confirming that every single one is genuinely, seriously dangerous. Is it the propulsion? Punishing, certainly a Euro, but it turns out to be the reason we haven't launched anything like this yet, not the specific reason a ship already underway would go on to die. Is it the sealed ecosystem, the closed loop of air and water and food that has to hold for centuries without a single outside resupply? Severe, unquestionably a Euro, but researchers keep finding, again and again, that closed biology, unlike almost everything else on this list, is at least partly genuinely engineerable, given enough time and effort. Is it the radiation, silently accumulating inside every living cell aboard for generation after generation? A real and serious threat, a Euro, but one that behaves less like a single executioner delivering a killing blow, and more like a quiet, compounding tax, patiently making every other problem on the ship measurably worse. The first surprise tonight is which suspect keeps surviving every single attempt to rule it out of contention a Euro, a candidate almost nobody names first when you ask them casually, hiding in the deeply unglamorous world of maintenance schedules and spare parts logistics. The second surprise is a piece of mathematics simple enough that a child could follow every step of it, and unforgiving enough that it explains, almost entirely on its own, why 5 separate problems that each sound individually survivable in isolation quietly become fatal the moment you ask all 5 of them to keep working together, simultaneously, for centuries on end, without a single one of them ever slipping. The third surprise is that one of the strongest remaining candidates for the real reason isn't a mechanical failure at all. It's an ethical one, a Euro, a genuinely uncomfortable question about whether it's even right to ask human beings who haven't been born yet to inherit a mission they never personally chose and can never physically walk away from. And the fourth surprise is the verdict itself. Once every single suspect has finally been given a fair and thorough hearing, not one single broken part, hiding somewhere in the design, waiting to be found and fixed. Something quieter than that, and considerably harder to solve with better engineering alone. By the end of tonight, you're going to understand exactly what the actual published research says kills a generation ship a Euro, and why the true answer turns out to be less like a single villain lurking in the machinery, and more like an entire, patient, unforgiving law of probability, quietly working against everyone aboard every single day, for as long as the voyage continues. This is not speculation dressed up as science. Every figure you're about to hear tonight is drawn directly from NASA's own technical assessments, from peer-reviewed engineering papers, from real closed ecosystem experiments actually attempted here on Earth, and from decades of documented human behavioral data gathered from the harshest, most isolated environments our species has ever deliberately chosen to occupy. This is what a genuine, careful investigation actually looks like once you refuse to let a single dramatic guess stand in for real evidence. Before we dive in, if you're someone who finds this kind of honest, unhurried exploration of the universe genuinely calming, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Before we can properly investigate why a generation ship would fail, we need to be honest with ourselves about the actual journey it would have to survive a Euro, because the true scale of it is remarkably easy to state in a single sentence, and genuinely difficult to feel in any meaningful way once you actually try. The nearest plausible destination is Proxima Centauri, and its known planet, Proxima Centauri b, sitting roughly 4.2 light-years from our own Sun. In NASA's public materials, this is consistently treated as the closest meaningful target for any conceivable future interstellar mission, a Euro, the nearest reasonably well-understood exoplanet in the entire catalogue of everything we've discovered. On a cosmic map, 4.2 light-years genuinely is close, practically next door by the standards of an entire galaxy stretching 100,000 light-years across. On any human scale, though, it is abyssal. Light itself, a Euro, the single fastest thing that exists anywhere in the known universe, outrunning everything else without exception, a Euro, still takes more than 4 full years just to cross that gap. A ship moving at any realistic speed we could plausibly build isn't simply planning a long trip, the way a transatlantic voyage or even a Mars mission would be. It's planning a voyage measured not in careers, not in single human lifetimes, but in dynasties, a Euro, an undertaking that spans the kind of time normally reserved for royal bloodlines and ancient religious institutions, not spacecraft. NASA's own interstellar propulsion assessment states the underlying problem with genuine bluntness. Using today's chemical rockets, a Euro, the exact same basic technology that carried every human being who has ever left Earth, from the first tentative suborbital hops all the way through the Apollo missions to the Moon, a Euro, a spacecraft could technically be placed on a trajectory pointed toward the nearest star, but the actual journey, at that technology's realistic cruising speed, would take approximately 70,000 years to complete. The same NASA assessment separately notes that a genuinely fast, human-relevant 40-year one-way flyby mission would instead require speeds in excess of 10% of the speed of light, a Euro, a velocity no human-scale spacecraft has ever come remotely close to achieving, or currently has any credible near-term path toward achieving. That single, stark contrast matters enormously for everything we're about to discuss tonight. The difference between merely leaving the solar system behind, technically, on some multi-thousand-year trajectory, and actually arriving while anyone aboard still remembers why the ship left home in the first place, isn't a modest, incremental engineering improvement you could reasonably expect a few decades of research to close. It's an almost incomprehensible leap in available energy and propulsion capability, a Euro, the kind of leap that separates difficult from not yet within the same order of magnitude as anything we've built. And when researchers finally stop assuming some convenient future miracle drive, and instead sit down and carefully model what a real, patient, fully multi-generational human voyage might actually require, using nothing but sober, defensible engineering and population genetics assumptions, the resulting numbers only grow stranger still. One of the most detailed generation ship population studies ever formally published, produced by researchers Rick Marin and Camille Belufi, works through the specifics of a full journey to Proxima Centauri b, lasting a genuinely staggering 6,300 years. That figure is not a typo, and it is not deliberate pessimism inserted purely for dramatic effect. It is simply, honestly, what the underlying problem actually looks like the moment you stop assuming an impossible engine and start asking, with real rigor, what a slow, patient, biologically realistic, multi-generational voyage would genuinely demand of everyone and everything aboard. In storytelling terms, a voyage of that length isn't really comparable to crossing an ocean at all. It's closer to launching an entire self-contained floating civilization and then quietly asking it to survive, intact and functioning, for a span of time longer than the distance separating the Bronze Age from the device you might be listening to this on right now. This, then, is the actual case file we're working from tonight. Not a quick trip that happens to go wrong somewhere along the way. A civilization-length commitment asked to hold itself together, coherently and continuously, for considerably longer than almost any human institution in recorded history ever has. It's worth pausing, briefly, on why any serious researcher would bother studying a scenario this extreme in the first place, rather than simply dismissing it outright as unworkable fiction and moving on to something more immediately practical. The answer is that a generation ship represents something close to a worst-case stress test for long-duration human survival a scenario so demanding, so unforgiving of any single weak link, that studying exactly where and how it would fail tells us something genuinely useful about every less extreme version of the same underlying problem. If researchers can identify precisely which systems break first, and precisely why, under conditions this severe, that same understanding directly informs far more modest, far more achievable goals. A multi-year Mars mission, a genuinely self-sufficient lunar base, or simply a better understanding of how our own single, shared, currently closed planetary system actually holds itself together. Every serious investigation into why a generation ship would eventually fail arrives, sooner or later, at the exact same short list of suspects: propulsion, closed ecology, mechanical reliability, radiation exposure, and the human beings themselves. All 5 of these are genuinely real dangers. None of them is exaggerated for dramatic effect, and none of them can simply be waved away with a clever engineering trick. But here is the detail that most casual conversations about this topic tend to miss entirely. These 5 suspects are not simply the same underlying problem, wearing 5 different costumes for variety. They are 5 genuinely, fundamentally different categories of difficulty, each one governed by an entirely separate branch of science, with its own separate rules, its own separate failure modes, and its own separate, hard-won body of research. Propulsion is, at its core, a physics and energy problem a question of how much raw force you can realistically generate, and precisely how much fuel that force ultimately costs you. Once every gram of that fuel has to be carried and accelerated alongside everything else. Closed ecology is a biology and control problem a question of whether millions of separate, interacting living systems, each with its own hidden feedback loops, can genuinely be kept in a stable, working balance for centuries without quietly collapsing into chaos the moment nobody's watching closely enough. Radiation is a mass and biophysics problem a question of exactly how much physical shielding material has to stand permanently between a fragile living cell and an unrelentingly hostile universe outside. Machinery is a reliability and maintenance problem a question of how long any physical object, however carefully engineered, can realistically keep functioning before it simply, inevitably, wears itself out. And social continuity is a political, ethical, and psychological problem all at once a genuinely different kind of question entirely, about whether human beings, across dozens of unbroken generations, can somehow keep choosing, freely and repeatedly, to cooperate with one another. A generation ship, in other words, is never really just one single machine that either works correctly or breaks down. It is, simultaneously, a power plant, a greenhouse, a fully staffed hospital, a sewage treatment facility, a dormitory, a school, a functioning legislature, and a carefully managed gene pool every single one of those institutions sealed permanently together inside one continuous pressure vessel, every single one of them required to keep functioning correctly, all at the same time, for centuries, without interruption, with absolutely no possibility of outside help arriving if any one of them begins to falter. This is precisely why the most careful, most rigorous researchers actually studying this exact question have moved steadily away from hunting for one single, dramatic, cinematic failure a euro, an exploding engine somewhere out in the dark, a catastrophic hull breach venting the ship's atmosphere in seconds a euro, and towards something considerably quieter and considerably more unsettling to actually sit, with what researchers call system of systems fragility. The genuinely interesting question was never really whether any one of these 5 problems exists in isolation. Of course it does. The far more interesting question is which one of them remains least solvable, even after every single one of the other 4 has already been pushed as far toward a workable, defensible solution as plausible future engineering could ever realistically allow. Think of it the way a careful medical examiner might approach a genuinely complicated case, rather than the way a detective in a simple mystery novel might. It's rarely useful, in a case this complicated, to ask, what single thing killed the patient? The far more useful question, and the one that actually leads somewhere productive, is which of the patient's several serious conditions was the one most resistant to treatment, even after every other condition had been successfully managed? That reframing a euro patient, methodical, resistant to the temptation of a single dramatic answer a euro, is exactly the spirit in which this entire investigation has actually been conducted across every serious paper we're about to walk through together tonight. Let's investigate each of these 5 suspects in turn, exactly the way the actual published research has. Let's start with the most obvious suspect on the list, because it genuinely deserves a full and fair hearing before we move on to anything else. NASA's own detailed review of interstellar propulsion technologies is refreshingly blunt about the current state of the entire field. For any genuinely relativistic interstellar journey a euro, one fast enough to matter on anything resembling a human timescale a euro. The only propulsion concepts considered worth serious engineering discussion at all are nuclear fusion, antimatter annihilation, directed energy sails, or some carefully engineered hybrid combining elements of all 3. Chemical propulsion, the exact technology that has carried every single human being who has ever left the surface of Earth, from Yuri Gagarin's first orbit through every Apollo mission and every shuttle flight since, simply isn't part of the conversation at all. It's not that chemical propulsion is merely inefficient for this particular job. It's that the entire technology sits in a completely different category of capability from what genuine interstellar travel would actually require. The gap between humanity's fastest current achievements and what real interstellar travel would demand is genuinely staggering, once you actually put concrete numbers beside each other. NASA's own review cites Helios 2, humanity's fastest spacecraft for several decades running, reaching roughly 0.024% of the speed of light during its closest approach to the Sun. The Parker Solar Probe, our current record holder, has pushed that figure up to approximately 0.067% of light speed a euro, genuinely remarkable, and still nowhere close to what's actually needed. A respectable, if still comparatively slow, interstellar mission requires something in the neighborhood of 10% of the speed of light. Depending on exactly which historic benchmark you choose to measure against, that's somewhere between roughly 150 and 4,000 times faster than the fastest thing our species has ever actually built and successfully flown. For a small, unmanned probe, weighing only a few hundred kilograms, this gap alone is already genuinely punishing to close. For an entire inhabited habitat a euro, one carrying living people, working farmland, radiation shielding, spare mechanical parts, and an entire miniature industrial base capable of manufacturing replacement components indefinitely a euro, the same gap becomes something closer to outright brutal. Acceleration energy scales directly, unforgivingly, with total mass. And even NASA's own review notes, almost as an aside, that pushing a single 720-kilogram unmanned probe to just 10% of the speed of light already implies an energy investment on the order of roughly 0.06% of the entire planet's total annual energy output. Read that again slowly. That's the entire energy cost for one small, unmanned probe. Not a floating city carrying thousands of living human beings and everything they would need to survive for centuries. And the leading candidate technologies that might one day close this gap remain, honestly, deeply, and genuinely immature, even after decades of dedicated theoretical work. Net energy controlled fusion, a Euro, a working reactor that reliably produces meaningfully more usable energy than it consumes to operate a Euro, has never once been demonstrated in any propulsion-ready, flight-capable form anywhere on Earth, despite well over half a century of serious, well-funded research effort. Antimatter, which remains, at least in principle, the single most efficient fuel that known physics currently allows, is so fantastically, almost absurdly expensive to produce and safely store that NASA's own technical assessment states plainly that our current production and storage capability would need to increase by a full 23 orders of magnitude a Euro, a factor of 10, multiplied by itself 23, separate times a Euro, before it becomes even remotely practical for any real mission to actually use. And directed energy sales, the underlying concept behind the currently active Breakthrough Starshot initiative, currently target roughly 20% of the speed of light a Euro, but explicitly, and only, for gram-scale robotic probes, riding sail structures on the order of a few tens of square kilometers, propelled entirely by a coordinated, ground-based array of phased lasers. Not for thousands of tons of crude habitat, farmland, and shielding. That antimatter figure deserves a moment of its own, because 23 orders of magnitude is easy to say and genuinely difficult to feel. It means our current best production and storage capability for antimatter would need to grow by a factor of 10, and then that new figure would need to grow by another factor of 10, repeated 23 separate times over, before it became remotely usable for a real mission. If you started today with the entire world's current annual antimatter production a Euro measured, at present, in mere nanograms a Euro, and doubled it every single year, it would take well over a human lifetime just to close a fraction of that gap, long before you even reach the finish line. So here, honestly, is the verdict on suspect number one after a genuinely fair hearing. Propulsion is very likely the primary reason we haven't already launched a real interstellar generation ship. It is probably not, on its own, the cleanest or most decisive reason a ship, once genuinely underway, would go on to eventually fail. What propulsion's fundamental limitations actually force is a specific, unavoidable choice. Either accept low, currently achievable cruising speeds in order to keep the ship's total mass even remotely manageable, or abandon the mission entirely before it ever leaves the drawing board. And the moment you accept those low, achievable speeds, the voyage's total length instantly explodes outward a Euro, from a handful of decades into full centuries, or, as we've already seen from Marin and Beluffi's own detailed modelling, into multiple full millennia. Propulsion, in the end, doesn't kill the ship directly with a single decisive stroke. It quietly hands the entire remaining problem over to everything else still waiting on our list a Euro, because it guarantees, unavoidably, the one single condition every other suspect fundamentally depends on to become dangerous at all: extreme, unrelenting duration. Closed ecology is very often assumed, almost instinctively, to be the obvious killer in any story like this one, and it's genuinely easy to understand exactly why that instinct exists. Living systems are messy. They're non-linear. They're absolutely riddled with hidden feedback loops and unexpected couplings that nobody, however careful, ever seems to fully anticipate in advance, no matter how much modelling gets done beforehand. The now famous cautionary tale here is Biosphere 2 a Euro, the ambitious, sealed, multi-biome research facility built in the Arizona desert, where a carefully selected team of 8 trained people lived, entirely and deliberately cut off from any material exchange with the outside world for a full 2 years. The facility's internal atmosphere's oxygen level unexpectedly, and quite dramatically, fell from a healthy 21% all the way down to just 15% euro, a drop severe enough that outside intervention became genuinely necessary to keep the crew inside safe and functional. The whole experience, by every account from those who lived through it, felt less like tending a carefully engineered, controlled greenhouse, and considerably more like watching a giant living lung slowly, mysteriously forget how to properly breathe. The deeper lesson researchers eventually drew from this wasn't simply closed ecology is fundamentally impossible. It was something more nuanced and arguably more useful. That large, genuinely diverse, partly self-organizing ecosystems can drift, quietly and unpredictably, in directions their own original designers never fully anticipated, no matter how carefully those designers thought they had planned for every contingency in advance. At the same time, serious, ongoing space life support research has moved well past the naive, almost romantic idea of simply packing a tiny, miniaturized version of Earth under a sealed glass dome and hoping, optimistically, that it somehow holds together on its own. The European Space Agency's ongoing MELSSA program is explicitly, deliberately designed to recycle air, water, and human waste continuously, while actively producing usable drinking water, breathable oxygen, and edible food, all through a carefully engineered chain of biological and chemical processing stages. NASA's own regenerative life support systems aboard the International Space Station already reliably reclaim approximately 90% of the station's total water supply a euro, recovering it directly from crew urine, from cabin humidity, and from sweat, and purifying it back into genuinely drinkable water. That figure is nowhere close to a fully closed, centuries-stable biosphere capable of running indefinitely without any outside input at all. But it stands as real, concrete, measurable evidence that closed-loop ecological engineering is a genuine, actively improving field of applied science, with real and growing partial successes behind it a euro, not simply an untested fantasy borrowed wholesale from science fiction. The underlying agricultural math itself is genuinely daunting, but at least, crucially, it's fully quantifiable, which matters enormously for planning purposes. Researchers estimate that a 500-person multi-generational crew eating a nutritionally balanced, reasonably varied omnivorous diet would need somewhere around 0.45 square kilometers of dedicated artificial farmland if the ship relied on advanced aeroponic growing techniques a euro, or as much as a full 1.01 square kilometers if it instead used more conventional soil-based farming methods. Either way, that's already the physical footprint of a small, genuine urban neighborhood, somehow carried entirely inside the hull of a single spacecraft. A vigorously active population of roughly 400 people, doing real physical work every day rather than sitting idle, would additionally need something on the order of 357 million kilocalories of food energy produced every single year, just to keep everyone aboard properly, sustainably fed and functioning at full capacity. What made the Biosphere 2 story so genuinely instructive, rather than simply embarrassing, was exactly how long it took anyone inside or outside the dome to properly diagnose what was actually happening. The crew initially assumed the falling oxygen levels reflected some kind of biological imbalance a euro, too much respiration somewhere, not enough active photosynthesis somewhere else, a straightforward accounting problem between living things breathing in and living things breathing out. It took careful, patient outside investigation to eventually trace the true cause to an entirely inanimate culprit, the facility's own structural concrete, quietly and continuously absorbing carbon dioxide directly out of the sealed air through an ordinary chemical process called carbonation, sequestering both carbon and oxygen permanently into the walls of the very building meant to keep everyone alive. Nobody had designed for that. Nobody had thought to model the building material itself as a living participant in the facility's overall gas balance. On a real generation ship, with no outside team standing by to diagnose a slow, silent gas leak of this kind, and no external oxygen supply available to simply pump in twice a year as a stopgap. A mistake this quiet could prove fatal long before anyone fully understood what was actually happening. So here, honestly, is the verdict on suspect number 2. Closed ecology is genuinely severe as a challenge. It is not, however, clearly singled out anywhere in the actual published literature as the one truly, decisively fatal reason a generation ship specifically would fail. The clear, consistent trend across real closed-loop life support research points firmly toward simplification, toward careful compartmentalization, toward constant active monitoring, and toward tight, deliberate control a euro, precisely because little Earths, left even slightly to their own natural devices, have repeatedly proven too ecologically slippery to simply trust on faith. Given sufficient mass, sufficient energy, enough distributed sensors, and enough accumulated biological expertise, ecology looks like a genuinely, seriously hard problem a euro, but at least a partially engineerable one, with a visible, if difficult, path toward gradual improvement. It's worth flagging honestly, though. No human-built system, anywhere, has ever yet demonstrated stable, genuinely multi-generational closure of this kind. That specific claim remains, honestly, still partly speculative. Everything researchers currently know about closed-loop ecology comes from experiments measured in months or single-digit years, extrapolated forward, carefully but unavoidably, into a regime nobody has ever actually tested directly. Here is where this entire investigation starts to feel less like troubleshooting a single, well-understood spacecraft, and considerably more like troubleshooting an entire immortal, self-contained city a euro, one that can never, under any circumstances, actually dock anywhere at all to receive real repairs. Researchers Andreas Hein and his colleagues, revisiting the genuine engineering feasibility of world ships in careful, systematic detail, are unusually direct about exactly where they believe the real, underlying danger actually lies. Their own stated conclusion holds that the primary feasibility issues facing a genuine world ship are economic in nature, and specifically, directly related to the ongoing maintenance system required to keep everything running. Their own precise estimate for what that maintenance burden would actually mean, in practice, is genuinely startling once you sit with it. A sufficiently large world ship may require a repair infrastructure capable of continuously detecting, replacing, and repairing individual failed components at a rate somewhere between 1 every 20 seconds and several separate repairs every single second, depending on exactly which underlying reliability assumptions get used in the calculation. Picture that specific image directly and let it settle for a moment. Not one dramatic, heroic wrench turn, performed occasionally in a dimly lit engine room whenever something happens to break down. A constant, continuous, unrelenting rain of microscopic component failures, scattered across an entire self-contained machine civilization, occurring every single second for centuries, without any conceivable pause. NASA's own separate reliability analysis for deep space habitats only sharpens this exact concern further still. It argues, in careful technical detail, that standard reliability estimation methods, a euro, the same kind of methods routinely used to certify aircraft or industrial equipment, or ordinary spacecraft for shorter missions a euro, are simply too weak, too imprecise, for genuinely long-duration missions of this kind, specifically because small, seemingly minor errors in the underlying assumptions about individual component failure rates can cause enormous, rapidly compounding collapses in a system's true overall reliability over time. And confirming those underlying assumptions with any real confidence would require actually running individual components continuously for periods of time considerably longer than anyone has ever genuinely tested them for in any laboratory, anywhere. NASA's own analysis goes so far as to state, quite plainly, that if current maintainability approaches and reliability modeling techniques remain fundamentally unchanged, it may not even currently be possible to build a habitat reliable enough for a comparatively modest human mission to Mars. Mars missions, remember, typically last somewhere around 1,000 to 1,200 days total euro, a few years at most. A generation ship demands this exact same still unresolved engineering logic, stretched not across years, but across full centuries. If our current reliability modelling approaches genuinely struggle to certify a habitat for a few years of Mars operations, extending that same unresolved uncertainty out across a multi-century voyage doesn't simply make the problem harder in a linear, predictable way. It makes the entire underlying modelling approach itself genuinely questionable, well before you've even accounted for a single specific component failure. Voyager offers, without question, the single best emotional counterexample available to us, euro, and remarkably, once you look closely, it actually reinforces this exact concern rather than easing it in any meaningful way. Yes, the twin Voyager spacecraft have now lasted an extraordinary 45 years in continuous operation, a genuinely astonishing achievement for any human-made object ever launched into space. But they are entirely uncrewed. They are not sealed, inhabited, living habitats requiring breathable air and drinkable water and edible food for living human beings every single day. Mission engineers have been systematically, deliberately shutting down entire non-essential onboard systems for decades now, one carefully chosen system at a time, purely to keep the remaining essential ones alive just a little longer. NASA has, on more than one occasion, brought long-retired engineering specialists directly back out of retirement, specifically to help interpret decades-old technical documentation that nobody currently working on the mission fully remembers how to properly read anymore. And the entire ongoing Voyager mission survives, to this day, only because of continuous, unbroken, active contact with Earth's full modern industrial and intellectual base euro, an entire civilization's worth of accumulated expertise on permanent standby, ready to help. A generation ship, by its very fundamental definition, could never have access to any of that. Not once, for the entire duration of the voyage. This is precisely why machinery emerges, on careful reflection, as a genuinely stronger candidate for the decisive failure mode than closed ecology turned out to be a moment ago. Ecology, given enough careful upfront design and sufficient ongoing monitoring, can at least sometimes be simplified down into tightly controlled, closely observed loops that behave predictably. Machinery, by direct contrast, simply ages euro everywhere, all the time, with absolutely no exceptions granted to anyone. Rubber and polymer seals slowly embrittle. Metal bearings gradually pit and wear. Solder joints fatigue under repeated thermal stress cycles. Lubricants chemically break down over time. Sensitive sensors slowly drift out of their original calibration. Pressure vessels quietly accumulate invisible structural damage with every cycle of use. And even the software specifically designed to monitor all of these gradual failures depends, ultimately and entirely, on physical hardware that is itself, continuously and unstoppably, growing older right alongside everything else. A generation ship wouldn't simply need a large supply of spare parts neatly stored away somewhere in its cargo hold. It would need genuine, functioning factories, continuous diagnostics, rigorous manufacturing standards maintained indefinitely, formal training programs teaching skills to engineers who haven't even been born yet, an entire, carefully preserved institutional memory, passed down deliberately from generation to generation, with absolutely no possibility, ever, of calling home for help when something goes seriously wrong. There's a genuinely recursive problem hiding underneath all of this, worth naming directly, because it's the detail that makes machinery such a strong candidate for the true, decisive answer to tonight's investigation. The machines responsible for manufacturing replacement parts will themselves, eventually, need replacement parts of their own. The machines responsible for building those replacement machines will, in turn, need spare parts too. At some point, the total industrial infrastructure required simply to keep the ship's basic systems running becomes almost as complex and almost as fragile as the ship's original systems themselves, a Euro, and the vessel quietly stops behaving like a conventional vehicle at all and starts behaving instead like an entire, self-replicating industrial civilization compressed down into a single sealed hull expected to sustain itself indefinitely with no outside supply chain of any kind. Interstellar space is not, in any meaningful sense, simply empty. It is a thin, cold, endlessly patient firing range of extremely high-energy particles, streaming continuously in every direction at once, a Euro, and unlike almost every other danger we've discussed so far tonight, it genuinely never, ever stops shooting. NASA's own Curiosity rover, during its own real, historical cruise from Earth to Mars, directly measured an average radiation dose of approximately 1.8 millisieverts per day, arriving specifically from galactic cosmic rays, even while the rover itself remained shielded inside a genuine, spacecraft-grade protective structure the entire time. NASA's own separate analysis notes that a full accumulated lifetime dose of 1 full sievert corresponds to roughly a 5% measurable increase in overall lifetime fatal cancer risk, based on careful long-term population health studies conducted here on Earth. Even at that comparatively modest, relatively short Mars cruise dose rate, the underlying arithmetic turns genuinely ugly remarkably quickly. The moment you stop measuring exposure in mere months and start measuring it honestly in full decades instead. And a generation ship voyage isn't measured in decades at all, it's measured in centuries. And it's worth remembering that a Mars-bound spacecraft, even out in deep space between the two planets, is still traveling comfortably inside the Sun's own broader protective bubble the entire time. Voyager's own direct measurements indicate that the heliosphere, a Euro, the Sun's own vast, extended magnetic bubble, continuously inflated outward by the pressure of the solar wind, a Euro blocks approximately 70% of all incoming galactic cosmic rays before they ever reach anything traveling within it. A genuine, true interstellar voyage leaves that entire protective bubble behind permanently, quite early in the overall journey, and never returns to it again. The ship isn't simply sailing out into a slightly rougher, more turbulent patch of sea. It's moving decisively out from behind an enormous, ancient breakwater entirely into fully open, completely unprotected water for the overwhelming remainder of the entire multi-century voyage. Why not simply add considerably more shielding, then, and be done with the whole problem once and for all? Because high-energy galactic cosmic rays turn out to be nasty in a very particular way that frustrates almost any straightforward, brute force engineering solution you might otherwise reach for instinctively. NASA's own detailed shielding analysis reports genuinely severe, diminishing returns as shielding mass increases. In one carefully modeled example, adding standard aluminum shielding up to a thickness of 3 to 4 grams per square centimeter produced essentially no measurable reduction in total radiation exposure whatsoever. Even a considerably thicker 30 grams per square centimeter of solid aluminum only modestly reduced the total absorbed dose, from roughly 210 milligrays down to approximately 190 euro, a genuinely disappointing improvement for that much added mass. Worse still, certain high atomic number shielding materials can actually generate dangerous secondary radiation of their own, produced directly by the violent impact of an incoming cosmic ray striking the shielding material itself and then fragmenting into a shower of smaller, sometimes equally dangerous secondary particles. In very real, very practical terms, a sufficiently thick protective wall can end up becoming part genuine shield and part unintended weapon, simultaneously, depending on exactly what it happens to be made of. So here, honestly, is the verdict on suspect number 4. Radiation is not trivially solved by any means currently available to us. It is also not, entirely on its own, obviously the single most decisive killer on this entire list either. It behaves considerably less like a single dramatic executioner delivering one final, decisive blow, and considerably more like a slow, vicious, endlessly compounding tax. More shielding always, unavoidably, means more total mass. More total mass always makes the already punishing propulsion problem meaningfully worse. More voyage duration always increases the cumulative radiation dose received by everyone aboard, and more ongoing maintenance is always required, indefinitely, for whatever specific shielding strategy eventually gets chosen for the mission. Radiation stands as one of the single clearest examples anywhere in this entire investigation of exactly why the generation ship problem, taken as a whole, is fundamentally multiplicative in nature, rather than simply additive or singular. It's genuinely worth flagging, honestly, that the precise long-term biological effects of chronic, decades-long, low-dose deep space radiation exposure remain, even today, an active and still largely unresolved area of ongoing scientific research. There are, in fact, two genuinely distinct categories of radiation hazard hiding inside this single problem, and they behave quite differently from one another, which matters for how a ship might realistically try to manage them. Galactic cosmic rays are a continuous, low-level background hum of extremely high-energy particles, arriving steadily from every direction at once, essentially impossible to fully shield against given the diminishing returns problem we just walked through. Solar particle events, by contrast, are sudden, intense, short-lived bursts of radiation, typically lasting hours to days, unpredictable in their exact timing but genuinely shieldable in a way galactic cosmic rays are not a small, heavily protected storm shelter built into the ship's core structure can meaningfully protect a crew during one of these events. The ongoing, unrelenting background hum is what accumulates quietly over decades and centuries. The sudden bursts are what could, in the worst case, deliver a dangerous, acute dose all at once. A generation ship has to defend against both simultaneously, using two entirely different strategies for the length of the entire voyage a continuous, passive shielding strategy for the slow background hum, and a dedicated, rapid response shelter strategy for the sudden, unpredictable bursts with no room to relax either one, even briefly, at any single point across the entire journey. If you had to identify which of these 5 suspects behaves least like a conventional, solvable engineering problem, this final one would be it. NASA's own Team Risk Evidence Report is remarkably direct on precisely this point. As space missions grow meaningfully longer, and as the surrounding isolation grows correspondingly deeper, genuine social cohesion among the crew matters considerably more, not less, with each passing month. Short missions, the evidence consistently shows, can often survive perfectly well on raw professionalism and narrow, disciplined task focus alone, without needing much else to hold the team together. Long missions, by sharp contrast, eventually come to depend on something considerably more fragile than professionalism on whether the people involved genuinely remain able to keep living together day after day, to forgive one another for real and accumulating grievances, to continue accepting legitimate shared authority, and to keep sincerely believing in the larger project they've collectively committed the rest of their lives to. The best real-world analog data currently available to us is genuinely tiny compared to an actual, full-scale generation ship but it still matters enormously for understanding the underlying pattern. Antarctic research stations offer one of the richest, most physiologically instrumented isolation datasets available anywhere on Earth. During the roughly 7 to 8 month Antarctic winter, stations are completely and totally cut off from the outside world No flights, no ships, no possibility of evacuation of any kind And in that stretch, otherwise healthy, carefully screened, professionally trained scientists reliably develop a documented condition researchers call winter over syndrome, measurable insomnia, cognitive impairment, irritability, and in some cases a genuinely eerie, mild dissociative state, where a person's attention simply drifts away mid-conversation for long stretches at a time. Even this analogue, demanding as it genuinely is, still ends. The winter always breaks. The planes always eventually return. Every person at that station knows, with total certainty, that their isolation carries a fixed, guaranteed termination date they can count down toward. A generation ship crew has no equivalent comfort available to them at all, for any generation except the very last one. Data gathered separately from HICEUS, a carefully run series of 8 to 12-month Mars isolation simulation missions conducted here on Earth, found that measurable psychosocial stress consistently ran highest during the earliest weeks of each mission, and then, notably, rose sharply again a second time, right around each individual mission's own natural halfway point. The researchers involved describe a distinct, recurring disruption phase, during which active conflict management noticeably becomes considerably more fragile and unreliable, precisely as the confinement itself continues to stretch on. And that specific pattern is what emerges after only 8 to 12 months of relatively comfortable, well-supported isolation. A genuine generation ship asks for this exact same, still fundamentally unsolved psychological problem to somehow hold together indefinitely a euro, not for one single, carefully screened and selected crew, but for the great-grandchildren of great-grandchildren, none of whom will have ever personally volunteered for any part of it in the first place. The relevant ethics literature sharpens this particular concern considerably further still. Researchers Stephen Umbrello and Angelo Balestreri argue, in careful philosophical detail, that later generations born aboard a generation ship may end up with genuinely little to no meaningful control over their own personal relationships, their own career paths, or their own reproductive choices, simply because the ship's continued long-term survival may come to depend entirely on strict, ongoing, centrally managed social control. In other words, the ship itself may only be able to survive, in practice, by gradually becoming deeply, structurally coercive toward its own inhabitants. The same careful analysis raises an even sharper, more genuinely uncomfortable point still. Those born aboard after the ship's initial departure are, in a very real and precise sense, effectively condemned to remain there for their entire lives a euro, locked permanently into a specific life project that was chosen, in full, by distant ancestors they will personally never meet and could never have consulted about the decision. This isn't a minor philosophical footnote, casually tacked onto the very end of an otherwise purely technical engineering report. It cuts directly, unavoidably, into the deeper question of long-term governance stability itself. A society that can only manage to preserve itself by steadily, continuously limiting the personal freedom of its own members may well succeed at the purely technical level, in the narrowest engineering sense, and still fail completely and catastrophically at the political and human level. There's a simple, memorable way of framing this particular asymmetry that captures the underlying problem with real precision. Steel does not become resentful, no matter how it's treated. Pumps do not quietly, privately ask themselves why they should have to spend an entire operational lifetime faithfully servicing a mission that won't actually arrive for another 20 full generations. Children, eventually, do ask exactly that question. This is precisely why so many serious, credentialed researchers and so many dedicated workshop studies specifically focused on long-duration interstellar habitation now treat genuine social cohesion, sustained personal motivation, and basic, ongoing human meaning-making as central, absolutely load-bearing engineering requirements in their own right a euro, not as decorative, secondary soft factors, politely mentioned only in passing at the very end of an otherwise purely technical report. It's worth being fully honest that this particular section of tonight's investigation is, by its very nature, partly inferential rather than directly proven. We simply have no genuinely centuries-long human spaceflight data of any kind whatsoever, anywhere. Every single relevant analog study we currently have access to runs for a matter of months at most. Not one of them has ever run for actual generations. There's a broader historical pattern worth sitting with here too, because it reinforces exactly this same concern from an entirely different angle. There is no period in recorded human history that we know of, anywhere on Earth, that lasted a full 250 years without some form of major war breaking out somewhere within it. The longest stretches of sustained peace any single region has ever managed still fall meaningfully short of that mark. A generation ship, considered purely in political terms, is a fully isolated city-state with no external enemies to unite against, no external allies to call on for support, absolutely no possibility of emigration for anyone genuinely unhappy with how things are being run aboard, and no possibility whatsoever of outside intervention if governance ever collapses entirely from within. Every single form of government human beings have ever actually devised a euro, monarchy, democracy, theocracy, oligarchy, and every variation in between a euro has, sooner or later, eventually failed, been overthrown, or been forced to radically transform itself, usually well within a few centuries at the very outside. A generation ship effectively demands a political and social system capable of remaining stable, broadly legitimate, and genuinely functional for longer than any political system in the entire recorded history of our species has ever managed, under conditions of total and complete isolation, with genuinely absolute stakes riding on every single failure. Here, finally, is the true mathematical heart of this entire investigation a euro, and it's genuinely simple enough that we can walk through every step of it together directly without needing any advanced mathematics at all. Suppose the ship's propulsion system continues working reliably across any given relevant stretch of time with some overall probability we'll simply call P. Suppose the closed ecological system holds together reliably with probability E. Suppose the ship's machinery keeps functioning properly with probability M. Suppose the radiation shielding continues to adequately protect everyone aboard with probability R. And suppose the crew's own social stability genuinely endures, unbroken, with probability S. The generation ship, taken as a complete, working whole, only survives if every single one of these 5 separate conditions holds true simultaneously a euro, which means the true overall probability of complete mission success works out to P multiplied by E, multiplied by M, multiplied by R, multiplied by S, sustained continuously and without interruption across the entire multi-century voyage. Here's precisely why that specific multiplication turns out to be so quietly cruel, once you actually sit with the numbers. Even if every single one of those 5 separate systems is, individually, genuinely excellent a euro, say, a full 99% reliable across any given relevant interval of time you choose to examine a euro, multiplying 5 separate 99% probabilities together does not, contrary to most people's first intuition, give you anything close to 99% overall reliability. It gives you something closer to 95% instead. And critically, that gradual erosion doesn't simply stop there at that first calculation and hold steady. Repeated across successive decades, and then across full centuries, that overall combined probability keeps eroding further and further, compounding relentlessly with every additional interval you add a euro. And this is all well before you've even attempted to account for the genuine unknown unknowns that no researcher, however careful and thorough, has yet thought to properly model in the first place. This single, remarkably simple piece of arithmetic is precisely why a generation ship tends to feel entirely, comfortably plausible in the opening chapter of the story, and then quietly, almost imperceptibly, becomes impossible by the time you reach the final appendix. Walk the arithmetic forward across real time, and the erosion becomes genuinely vivid. If each of those 5 systems holds at 99% reliability across any given decade, the combined probability of all 5 holding together simultaneously for that same single decade comes out to roughly 95%, exactly as we just calculated. Extend that same combined 95% per decade figure across 25 consecutive decades a euro. The 250 years several of tonight's own studies use as a working baseline a euro, and the overall probability of the entire mission surviving intact, start to finish, without a single one of those 5 systems ever slipping outside tolerance, falls to somewhere in the low single digits. Not because any individual decade was especially dangerous on its own. Simply because the same modest risk, repeated patiently enough times in a row, eventually catches up with almost any system, no matter how well built it originally was. The existing literature keeps warning about exactly this specific pattern, explicitly and repeatedly across multiple independent studies. Marin and Beluffi's own detailed demographic modelling arrives at a minimum viable crew size of just 98 people for their specific 300-year Proxima Centauri b scenario a Euro. But their own published paper is genuinely careful to state, in plain language, that this particular figure deliberately omits the effects of ongoing mutation, internal migration, genetic selection pressure, random genetic drift, cumulative cosmic ray genetic damage, and any outright ship operation failures of any kind. It represents a conservative lower bound, calculated under deliberately generous assumptions a Euro, not any kind of firm, reliable guarantee of actual long-term success. The farming area estimates we walked through together a little earlier tonight carry this exact same honest caveat, built directly into their own methodology. They represent constraints drawn from one specific, isolated model, embedded inside a much larger, more complicated web of interacting assumptions a Euro, not a comprehensive, full mission guarantee that literally everything else aboard will also, simultaneously, continue to hold. This is precisely why the true real reason a generation ship would eventually fail is almost never hidden away inside any single subsystem, quietly waiting there to be discovered by a sufficiently clever engineer. It lives instead in the simple, genuinely unforgiving demand that every single subsystem remain reliably within tolerance, all at the same time, continuously, for a total duration considerably longer than any closed human-built system has ever actually managed to sustain before. A generation ship is, in this precise sense, a relay race in which every single runner across every single generation must perform essentially perfectly for a total span of time longer than the entirety of recorded human civilization has yet managed to endure. One single failed crop cycle can meaningfully stress the ship's entire social order. A stressed social order can, in turn, quietly impair overall maintenance discipline. Impaired maintenance discipline can gradually degrade the integrity of the ship's radiation shielding. Degraded shielding can measurably affect long-term crew health and fertility rates. And these various risks don't simply add together in any neat, predictable, linear way, the way a hopeful engineer might initially wish. They actively couple with one another instead, feeding directly and continuously back into each other in exactly the compounding pattern this entire investigation keeps circling back around to again and again. The single clearest, most explicit statement to emerge anywhere from this entire body of published research comes directly from Hine and his colleagues' own paper. The main world ship feasibility issues are rather economic and related to the maintenance system. That specific sentence carries genuine, substantial weight, precisely because it comes from a paper actively, deliberately trying to revisit and honestly re-establish genuine mission feasibility a Euro, not simply offering casual speculation for its own sake. It deliberately, consciously pushes attention away from one-time, dramatic launch heroics and firmly toward the permanent, deeply unglamorous burden of keeping an entire artificial world reliably functioning, indefinitely, without any meaningful pause, for as long as the mission continues. NASA's own separate interstellar propulsion review doesn't contradict that particular conclusion in any way. If anything, it complements it directly. The report is, for the most part, primarily concerned with exactly how difficult it genuinely is to reach another star system quickly at all using any technology currently available or plausibly foreseeable. Generation ships, as an entire concept, exist specifically because that particular ambition a Euro arriving quickly, within a single human lifetime a Euro, has already been quietly, deliberately abandoned from the very outset. And the moment that specific concession is made, The moment's speed itself is sacrificed purely to keep the ship's total mass even remotely manageable. The entire decisive pressure shifts immediately and completely away from propulsion and directly toward duration-driven system survival instead. The ecological literature we walked through earlier is genuinely sobering, honestly. But it isn't final or conclusive either way. Biosphere 2 exposed, in uncomfortable and very real detail, exactly how unpredictably complex closed systems can quietly drift over time, even under expert supervision. The International Space Station's own regenerative systems, alongside ESA's continuing Melasesa research program, together demonstrate that meaningful partial regenerative closure is genuinely real and steadily, measurably improving with each passing year of research. Taken together, that specific combination of evidence suggests that closed ecology represents a major, genuine, serious challenger Euro, but not, on its own, obviously the single most fundamental problem sitting at the very center of this entire investigation. The human factors research and the ethics literature, by clear contrast, point more directly than anything else we've covered tonight toward the single least engineerable variable on this entire list. NASA's own evidence base shows plainly that overall mission success depends more and more heavily on genuine social cohesion as mission duration continues to grow longer. Generation ship ethics research emphasizes, repeatedly and consistently, the sharp, genuinely unresolved tension between overall mission survival and individual personal autonomy, stretched thin across generation after generation of people who never personally consented to any part of the arrangement in the first place. None of this evidence definitively, conclusively proves that human society itself is the single decisive failure point, standing clearly above every other candidate on the list. But it does demonstrate, quite clearly and consistently, that human governance is the one variable, among all five, least likely ever to fully submit to a clean, purely technical engineering solution. If you force this entire investigation down to a single engineering answer, it comes out as maintenance and long-term mechanical reliability. If you force it down instead to a single human answer, it comes out as social and governance stability, sustained across many successive generations. And if you force it down to a single systems-level answer a Euro, genuinely the one most faithful to the full weight of the available evidence, taken together as a whole a Euro, it comes out as the steadily compounded probability of failure, patiently accumulating, year after year, across an extreme and unrelenting duration. It's genuinely worth noticing what this careful synthesis does not conclude, because the absence is just as informative as the presence. No credible researcher in this entire body of literature argues that the ship would fail from a single dramatic engine malfunction, or a single catastrophic hull breach, or any other single cinematic event of the kind popular fiction reaches for instinctively. That absence is itself a finding. The real danger these researchers keep converging on isn't a moment. It's a duration a Euro, the simple, patient accumulation of ordinary, individually survivable risk, repeated across a timescale longer than anything a human civilization has ever actually been asked to sustain before. Before we deliver the final verdict, let's gather everything we've uncovered tonight, all together in one place, and actually sit with the true scale of it. A journey of 4.2 light years, requiring, at any propulsion technology we currently possess, somewhere between 70,000 years and 6,300 years to complete, depending entirely on assumptions this investigation has spent the last several minutes carefully testing. A propulsion gap so severe that pushing a single 720 kilogram probe to just 10% of light speed already costs something on the order of 0.06% of the entire planet's annual energy output a Euro for a probe, not a habitat. A closed ecosystem that has never, in a single real-world attempt anywhere on Earth, sustained even 8 carefully trained people for more than 2 years, let alone tens of thousands of people for multiple centuries. A maintenance burden so relentless that a sufficiently large world ship may need to repair a failing component every 20 seconds, or faster, forever, with no factory back home to call. A radiation environment so severe that even the best shielding physics currently allows produces only modest, disappointing reductions in exposure, while occasionally generating dangerous secondary particles of its own. A social and ethical burden asking entirely unborn generations to inherit, without their own consent, a mission stretching far beyond any single human lifetime. And beneath every one of these individual numbers, a single, unforgiving multiplication. 5 systems, each excellent in isolation, compounding down toward failure the moment they're all asked to hold together at once, for longer than recorded civilization has yet endured. Every one of these figures, examined completely on its own, sounds like a single, isolated obstacle a euro, difficult, certainly, but survivable with enough careful engineering. Taken together, multiplied against one another rather than simply added, they describe something closer to a message, quietly encoded directly into the physics, the biology, and the psychology of the problem itself. Not yet. Not never. Not yet. There is a real and important difference between those two words, and this entire investigation has been, in its own quiet way, an argument for taking that difference seriously. Never is a claim about the fundamental structure of reality a euro, about laws of physics that cannot, under any circumstances, be worked around. Not yet is a claim about the current, temporary limits of one particular species' accumulated knowledge at one particular moment in its own history. Every single figure gathered together in this section tonight belongs firmly to the second category, not the first. So, after a full, fair, and thorough investigation of every genuine suspect a euro, what is the real reason a ship to another star would never actually survive? The most honest answer currently available is this. A generation ship was never really just a vehicle in any simple, conventional sense. It is, more precisely, a fully sealed civilization, quietly asked to remain technically competent, biologically balanced, politically legitimate, and psychologically stable, continuously for a span of time stretching from full centuries into genuine millennia. Serious, careful research doesn't reveal one single, cartoonishly dramatic fatal flaw, conveniently hiding somewhere specific in the overall design, just waiting patiently to be discovered and fixed by a sufficiently clever engineer. It reveals something considerably quieter than that instead, and considerably more genuinely unsettling to sit with honestly. The entire mission grows measurably harder every single time you make it even slightly more realistic. Lower the cruising speed in order to make the propulsion problem even conceivable in the first place, and the total transit time immediately stretches outward from mere decades into entire eras. That single, seemingly reasonable concession, in turn, directly magnifies the total maintenance load required, deepens the underlying ecological drift, multiplies the cumulative radiation dose received by everyone aboard, meaningfully accelerates institutional decay over time, and significantly intensifies the genuine moral strain involved in asking entirely unborn future generations to faithfully serve a mission they never, personally, freely chose for themselves. If this entire investigation had to be distilled down honestly into a single sentence, it would be this. A generation ship would ultimately fail not because of any one single broken part, hiding somewhere specific in its design, but because its true underlying mission was never really just crossing physical space in the first place. Its true mission, all along, was preserving an entire, fully functioning human world, sealed permanently inside a single machine for considerably longer than any human world, or any human-built machine, has ever actually managed to remain genuinely stable before. That is precisely why the deepest, most genuine obstacle uncovered by this entire investigation is best described, with real honesty, as compounded long-duration fragility a euro with maintenance and reliability, and human social continuity, standing out clearly as the two single most unforgiving terms in the entire unforgiving equation. It's worth being precise about what this verdict does and does not actually claim. It does not claim that interstellar travel itself is forever impossible, in some absolute, unchangeable sense written permanently into the laws of physics. Every single obstacle catalogued across this entire investigation is a gap in our current knowledge and current engineering capability, not a fundamental law standing eternally in the way. It claims something more specific and honestly more useful, that with the technology, the biology, and the social science we currently possess, the mission fails not at any one identifiable point, but through the slow, patient, compounding accumulation of many individually survivable risks, sustained across a duration longer than any closed human system has ever actually been tested against. There's something genuinely worth sitting with directly here, now that this entire investigation has finally reached its conclusion. This was never really a story about spaceships specifically, not at its true underlying core. It's actually a story about what inevitably happens to any sufficiently complex system, of essentially any kind at all, when it's asked to keep every single one of its many interdependent parts functioning correctly, all simultaneously, for considerably longer than it was ever originally designed or expected to last. The exact same compounding mathematics that quietly dooms a generation ship a euro 5 separate systems, each individually excellent on its own terms, multiplying steadily downward toward eventual failure the moment they're all asked to hold together simultaneously, for centuries without pause a euro, applies with genuinely real force to entire civilizations, to lasting institutions, to long marriages, to, essentially, any long-lived human project genuinely worth naming or attempting in the first place. And there's a quiet, genuinely important distinction hiding underneath all of this, worth carrying forward carefully. A generation ship is, necessarily and by its very nature, an entirely designed system a euro, every redundancy carefully planned well in advance, every safety margin deliberately calculated ahead of time, every individual part engineered precisely to a specification some particular person or team consciously chose beforehand. Earth's own living biosphere, by sharp contrast, was never designed by anyone at all in any comparable sense. It evolved instead, slowly and patiently, across a full 3.8 billion years, through countless overlapping, genuinely redundant, endlessly self-correcting relationships between millions upon millions of separately interacting species, none of them ever following any single, unified master blueprint handed down from above. That specific difference may well be the single most important insight buried inside this entire investigation. Designed systems, like a generation ship, tend to fail cleanly, and in series, precisely the way Hein's own maintenance mathematics predicts they eventually will. Evolved systems, like Earth's biosphere, fail far more messily when they do fail a euro, but they also, remarkably, tend to root quietly around accumulated damage in ways no engineer, however brilliant or careful, has ever yet fully learned how to deliberately replicate on purpose from first principles. We are, quite simply, not yet the kind of civilization that fully knows how to build something genuinely as resilient as the one single thing we all happen to already be standing on. There's a genuinely useful reframing hiding inside this specific observation, worth carrying forward carefully. Every single gap this investigation uncovered tonight a Euro closed-loop ecology that doesn't quietly poison itself, maintenance systems that can genuinely sustain themselves without outside supply, shielding that protects without becoming its own hazard, governance that survives longer than any government in recorded history, and a genuine, freely chosen sense of shared purpose that somehow manages to survive being handed down across generations who never personally agreed to inherit it a euro. Every one of these is a problem worth solving for reasons that have nothing at all to do with reaching another star. They are, each of them, versions of problems our own civilization is already quietly working through, right now, on the one world we currently have. A generation ship, in that sense, isn't really asking us to invent something entirely new. It's asking us to become dramatically, comprehensively better at things we already, urgently, need to be better at anyway. Picture it, one final time, before we bring tonight's investigation to a close. Somewhere in an unbuilt, still entirely hypothetical future, a ship eventually departs, carrying thousands of living people, none of whom will ever personally live to see the star they're patiently traveling toward. Every single system aboard has to keep working correctly, all at once, continuously, for full centuries without any real pause. The closed ecology, quietly and continuously cycling nitrogen and carbon and clean water through machinery that must never once fail completely for any meaningful length of time. The radiation shielding, standing permanently between fragile, irreplaceable human cells and an unbroken, endless rain of high-energy cosmic particles arriving from every direction. The dedicated maintenance crews, steadily replacing failing components at a rate approaching 1 every 20 seconds, forever, with no distant factory back on Earth left to call for spare parts when something eventually runs out. And the people themselves, generation after generation, none of whom personally chose this particular life for themselves, each one somehow still managing, against real odds, to find their own reason to keep genuinely believing in a destination they will personally never live to see with their own eyes. Every single one of these individual systems, examined carefully and honestly, entirely on its own, looks genuinely survivable in isolation. That specific fact is precisely what makes the final verdict land as hard as it ultimately does once you see the whole picture together. It was never really any single, obvious, dramatic point of failure waiting there to be found. It was always, from the very beginning, the simple, quietly unforgiving demand that absolutely everything keep working correctly, together, all at once, for considerably longer than anything our entire species has ever actually managed to keep working before in the whole of recorded history. We don't yet fully know how to run that particular relay race all the way through, without some single runner eventually, somewhere along the way, stumbling. Not for centuries. Not yet. But understanding precisely where and precisely why each individual runner would most likely eventually fall a euro, that itself is not defeat, and it was never meant to be. That is, instead, genuinely the very first real step towards someday actually building a baton sturdy enough to survive being carefully passed, unbroken, from one steady hand to the next, across considerably more generations than any of us listening tonight will ever personally meet or come to know by name. And there is something genuinely worth holding on to in the very fact that this investigation could be conducted at all a euro, that real researchers, working across genuinely separate fields of propulsion physics, closed system biology, materials, engineering, radiation science, and human ethics, could sit down together, compare their separate findings honestly, and arrive at a shared, coherent verdict, rather than 5 competing, disconnected opinions shouted past one another. That itself is a small, quiet demonstration of the exact kind of long-term, cooperative thinking a generation ship would eventually need in far greater supply. We are, even now, tonight, already practicing a small piece of the very thing the ship would ultimately require of everyone aboard it. Tonight we carefully investigated the real reason a ship to another star would never survive. And the honest verdict, once every suspect had finally been given a fair hearing, turned out to be considerably more precise and considerably more genuinely instructive than any single dramatic answer could ever have been on its own. We found that propulsion, however genuinely punishing as a challenge, is mostly the reason we haven't launched anything like this yet a euro, not, on its own, the single cleanest reason a ship already underway would eventually fail. We found that closed ecology is severe as a problem, but at least partly engineerable through careful simplification and tight ongoing control, unlike some of the other suspects that followed it later in our investigation. We found that machinery Euro, the deeply unglamorous, quietly persistent problem of long-term maintenance and mechanical reliability Euro, emerged as one of the two single strongest candidates for the true, honest answer, requiring active repairs at a rate approaching several every single second, sustained indefinitely, with absolutely no possibility of ever calling home for help. We found that radiation behaves considerably less like a single dramatic executioner, and considerably more like a slow, compounding tax, actively multiplying every other risk aboard the ship rather than simply standing alone as its own isolated threat. And we found that human society itself, Euro, genuine social cohesion, functioning governance, and the deeper underlying ethics of asking entirely unborn future generations to inherit a mission they personally never chose for themselves, Euro, is the single least engineerable variable in this entire careful investigation. And underneath all 5 of these individual suspects, working quietly together the entire time, we found the true, honest verdict. Not one single broken part, hiding somewhere specific in the design, but the simple, genuinely unforgiving mathematics of steadily compounding probability, demanding that absolutely everything survive together, all at once, continuously, for considerably longer than any human system Euro, whether carefully designed or patiently evolved Euro, has ever actually, genuinely been tested before. A generation ship would ultimately fail not because crossing the raw physical space itself is somehow impossible, but because preserving an entire, fully functioning human world inside a single sealed machine continuously for centuries on end turns out to be a considerably harder problem than crossing that same space ever actually was on its own. None of this, taken as a whole, is really a story about failure for its own sake, or a story designed simply to close a door and walk away from it. It's a story about precision Euro, about the genuine value of naming, honestly and specifically, exactly where a beautiful, ambitious idea currently runs into the limits of what we actually know how to build, rather than simply waving vaguely at the difficulty of space travel and leaving it there. Every single suspect this investigation examined tonight, Euro, the engines, the sealed ecosystem, the machinery, the radiation, and the people themselves, Euro, remains, in its own way, an active, ongoing area of real scientific effort, inching forward year by year, decade by decade, toward answers nobody currently has in hand. Sleep well tonight, resting on the one single world we currently know of that has already, quietly, run this exact same experiment successfully, not through any careful, deliberate upfront design at all, but through a full 3.8 billion patient, genuinely redundant, endlessly self-correcting years, without ever once needing to reach a final verdict on precisely why it might eventually fail. Good night, and rest well under the stars and under the quiet, ongoing, patient work of everyone, everywhere, still genuinely trying to learn exactly what it would actually take to build something worthy enough to finally carry us there.